current electricity topic, this section is about series circuits. So what is a circuit? A circuit is a closed, that's going to be a very important word, we'll talk about that, conductive path. The path is usually by wires, right, through which a current may flow. Now, just briefly about current, we have conventional current that flows from positive to negative. In actuality, what's happening is that electrons are flowing from negative to positive. And we have Benjamin Franklin to thank for that little discrepancy. We will put the blame squarely on Benjamin Franklin, because back in 1750, when he first called current positive, he didn't see 150 years into the future that J.J. Thomson was going to discover the electron and call it negative. Bad Benjamin Franklin for not seeing 150 years into the future. So we stated that a circuit has to be closed. It has to start and end in the same place. Now, circuits in general start from the positive terminal of a source of electricity, like a battery, a wall outlet, a power supply, etc. So if I start drawing a simple circuit, all right, here's the positive terminal of a battery, right, the longer line, positive, negative, positive, negative, all right, so here's the positive, here's the negative, and I can have the wire extending out from the positive. I'll put in one little resistor, right, and then go right back to the battery, thus closing the circuit. The circuit has to be closed. It has to start and end in the same place. Keep in mind again that conventional current, all right, I, is defined as the flow of positive charges, which isn't really happening, right, but we go from positive toward negative. Keep in mind that what's really happening is that electrons are going away from the negative and toward positive. So the electrons are actually going this way. Okay, now this is not a problem, don't even worry about it. Generally speaking, we're going to use the direction of conventional current whenever we talk about circuits. Right, now, what happens is that the current flows out from the source of electricity through various components like resistors, light bulbs, diodes, whatever they're flowing through. You could have a refrigerator in here, you could have a microwave in here, you have wires all over cars. There are big, thick, what they call wiring harnesses with maybe 20 different wires coming off the battery and going off in all different directions, powering all different aspects of what's going on in the car. The windows rolling up and down, right? The headlights coming on and turning off. There are circuits and we go right back from the positive right back to the negative in all those cases. Now, there are circuits inside of all electrical devices, all the wires inside the refrigerator, inside the television, inside your microwave, right? All of these devices. As I said before, the car has a wiring harness with lots and lots of wires with circuits flowing through them. There are tiny electrical circuits imprinted onto computer boards, onto the motherboard, right? Little chips, computer chips, have little circuits etched into them. They can be very, very, very tiny. As a matter of fact, nowadays, some of those chips are virtually microscopic, right? So they're tiny little chips. And the electricity is traveling around the motherboard, going all to the different components on the motherboard, right, and imprinted onto the tiny little computer chips. Things are getting smaller and smaller and smaller. That's been happening for decades now. The circuits, the tiny circuits printed onto the motherboards of computers and into the chips, those little circuits might be made out of trails of copper, silver, gold, or other conductive materials etched into that board or into the chip. Regardless of whether you're talking about a physical wire or a physical trail of copper etched into a circuit board, right, or a chip, keep in mind all of these circuits, the big ones, the small ones, have to be closed. They have to start, go around, and end in the same spot. And as you're going to see, as we talk about series circuits, and then in later videos as we talk about parallel circuits, the circuit is going to have to be closed, starting and ending in the same starting, going around, powering whatever it's going to power, and then coming right back to the same place, in this case, back to the battery. Let's review some of the circuit symbols that we already learned and introduce some new ones. All right, a cell. All right, a cell would be drawn as one positive and one negative. A battery would be two or more cells. So we could have one positive, one negative, and one positive and one negative. So that's a cell, that's a battery. A resistor, you know, is a jagged, all right, that's probably too many teeth. A wire is just a line. Of course, that line could be going across or up and down or pretty much in any direction. Now, a switch, right? If the switch is open, right, it's going to look like this. Right? This switch is open. The electricity cannot go through. Right? If the switch is closed, then the electricity can go through. So you take that switch and push it down so that it's closed, right? And now the electricity can flow again. Right? An open switch, a closed switch. A light bulb. The symbol for a light bulb is a circle, right, with a squiggle like that in the middle to represent the filament inside of an old incandescent light bulb. Now, I'm going to draw the voltmeter a little bit differently than what you would see on your reference tables to emphasize the fact that voltmeters are always connected to what they are measuring in parallel. So I'm going to draw the voltmeter like this. All right, there's the V for voltmeter. And instead of making a straight line, I'm going to put it around, right, what it's measuring. Now the ammeter, all right, one more time, the voltmeter, all right, is, all right, around what it's measuring. Now the ammeter, all right, is a circle, all right, and in a straight line, all right, in series with what it's measuring. All right, so these are all the circuit symbols that you'll probably be coming across in the current electricity topic. You should try to memorize them, although you'll certainly remember them after you get used to using them in various series and parallel circuit problems. All right, so let's start with a simple definition of a series circuit. Copy this down. A series circuit is a circuit in which the electrons have only one possible path. There's no place where the mob of electrons can split up and head off in different directions. They all have to follow the same path. So would you now draw a series circuit with a 60-volt battery and two 3-ohm resistors? So here's the battery, all right? Positive, negative, positive, negative. I'm putting the positive on top and the negative on the bottom because we're going to have our current go this way, our conventional current go this way. All right, so here's our first resistor, all right, and we'll put our second resistor over here. Okay, and then back to the battery. Now, every component in a circuit, the battery, the resistors, the light bulbs, any devices that you're using, the refrigerator, the microwave, etc., have their own voltage, all right? So the battery has its own voltage. They have their own current, I. They have their own resistance and their own power. Now, in this video, I'm not going to calculate the power. It's not hard. I just don't want this video to get too long. Right? We'll calculate the power in a later video. All right, so every single component has verb. All right, now, for the battery, we're going to call this the total voltage, VT, the total current, the total resistance, and the total power. All right, now here we are for resistor number 1. All right, resistor number 1 has its own voltage, has its own current, has its own resistance, and has its own power. V1, I1, R1, P1. This is resistor number 1. So that's why we're labeling it voltage 1, current 1, resistance 1, power 1. This second resistor here has its own voltage, so that's V2, right? Its own current, that's I2, its own resistance, right, and its own power. Right? So we can either be told or calculate the voltage, the current, the resistance, and the power for each component. Now, we started this question by saying that the total voltage, and the total voltage is always the voltage of the battery or the power supply, was 60 volts. And we also said that there were two identical 3 ohm resistors. 3 ohms, right? And here the resistance is 3 ohms. Right, so this is how we're going to start. Okay, so get that all copied down. All right, and we'll be moving on. You're going to need your reference tables to look at equations. We're going to be moving on to showing the equations that we're going to use to figure out all of the other variables here, all the V's, all the I's, all the R's for each of the components based upon the information that we have so far. So pick up your reference tables and open up to the electricity page, and let's copy down all the equations that pertain to series circuits. All right, in the reference tables, it's going to say series circuits. All right, it's not going to say equations. I put that there. Series circuits, okay? And we're going to copy down the equation for current, the equation for voltage, and the equation for resistance. All right, so what you have, now I'm going to add capital T's for total. The total current in a series circuit is going to be equal to the current through the first resistor equal to the current through the second resistor. In other words, what this equation is telling us is that in a series circuit, all the currents are the same. Now, voltage, right? The total voltage, and I'm going to put V total. The total voltage in a series circuit is going to be the voltage through the first resistor plus the voltage through the second resistor. Now, if there were more resistors, then it could be I3 and I4 or plus V3 plus V4. We would just keep going if there were more than 2 resistors. Now, the total resistance, they write REQ. That means equivalent resistance. It's the same thing as saying the total resistance. I like to use total. Some people like to use equivalent. It just doesn't matter which one you write. Okay, so the total resistance is going to be just like voltage. You're going to add up, right, the resistance for the first resistor plus the resistance from the second resistor. If there's a third resistor, plus R3, plus R4, etc. So these series circuit equations tell us that all the currents are the same. The voltage equation, the total voltage equation, tells us that the total voltage is the sum of the voltages of all the components, mostly resistors, possibly light bulbs. And the total resistance is the sum, you add them up, of all the resistances of all the components. It could be resistors, could be light bulbs, etc. Now, one more equation that we're going to need to work with circuits to figure out all the voltages, all the currents, all right, and all of the resistances in a series circuit, all right, or a parallel circuit for that matter. We're going to need Ohm's Law. So on your reference tables, there is R equals V over I, all right, and that is Ohm's Law. All right, so get those copied down, and I'm going to talk a little bit about one rule about using Ohm's Law in just a moment. Here's a little rule that you have to remember for using Ohm's Law. Make sure you copy this rule down. Always use subscripts, and always put the same subscript for V, I, and R. Let me show you what we mean. All right, if, for example, you want to calculate the resistance of the battery, all right, the total resistance, right? That's going to be R equals V over I. You're going to take the total voltage and divide it by the total current. Notice that all of the subscripts are the same. Okay, what if you wanted to find the voltage for resistor number 1? That would be V1. Now V, if you cross multiply, right, V times 1, put the R over 1, right? V times 1 equals R times I. All right, so V is going to be I times R. But since you're trying to find the voltage for the first resistor, you want the current through the first resistor times the resistance of the first resistor. All right, now that's not to say that sometimes I total is going to be the same as I1. All right, but if you keep this all straight, it's going to be much, 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 much easier in the long run, and you won't get confused when you've got maybe 12 different variables or more that you're trying to find. Let's try one more. All right, what if you're trying to find the current, all right, I. Now remember, you can, right, these are inversely related, R and I, so you can switch them. All right, so I would be equal to V over R. What if you're trying to find the current in the third resistor? All right, so the current through the third resistor, I3, would be the voltage across the third resistor divided by the resistance of the third resistor. So the rule for Ohm's law, always use subscripts and always use the same subscript for all three of the variables. All right, that'll make it much, much easier and you won't make mistakes. We're back to the series circuit problem that we started a couple of minutes ago. Now let's again fill in the information that we were given at the beginning of the problem. They told us that the total voltage, that's the voltage in the battery, was 60 volts. We were also told that each resistor was 3 ohms. All right, so that resistor R1 and R2 are each 3 ohms. Now, we need to calculate all the rest of the variables. I'm just going to leave out power. We're not going to do total power, P1, P2. All right, we'll do that in a different video. All right, so using those equations that we just looked at, the equations for total current, total voltage, total resistance, and Ohm's law, is there anything you can think of that we can do right now? We've got V total, we've got R1 and R2. I hope you're thinking that you can take R1 and R2, add them together, and get R total. So let's do that now. All right, for a series circuit, R total is going to be R1 plus R2. So we've got 3 ohms plus 3 ohms. So that means that R total, all right, is going to be 6 ohms. Okay, since we were started with R1 and R2, what are we going to do? We're going to add them together and get R total. All right, so here we go. 6 ohms. Now, what can we do next? I'll give you a hint. You can use Ohm's law. All right, Ohm's law, R equals V over I. Now, are you going to use it for the first resistor? Do you have enough information here? Probably not. Second resistor, no. But look at the totals. All right, you can find I total because you have V total and R total. So we're going to switch I and R. All right, switch the inverses. So I equals V over R. And we're trying to find I total. So it's going to be I total equals V total over R total. So we're going to take plug in V total 60 volts, R total 6 ohms, 60 volts over 6 ohms, all right, and that's going to be 10 amps, all right, 10 amps. So there's your current. That's a lot of current. All right, we're just trying to use numbers that are going to make this easy, not necessarily terribly realistic. All right, so I total is 10 amps. All right, now, remember that in a series circuit, all the currents are the same. Remember that I total equals I1 equals I2. So if the total current is 10 amps, then I1 is 10 amps, and I2 is 10 amps. And go ahead and fill those in now. All right, so we're really starting to move here. All right, now, we've got everything. We're not going to do the power, but the last thing we need to do is the voltage for each resistor. We don't know V1 or V2 yet. All right. Now, I will say this. No, all right, let me hold that off. All right. Let's use Ohm's Law. Okay. V equals I times R. Right? We know that R is V over I, but if we cross multiply, V times 1 equals I times R, right? Then we'll get this version of Ohm's Law, right? V equals I R, and we can do that for the first resistor, V1 equals I1 R1, and for the second resistor, V2 equals I2 R2. Okay? So, I1 is 10 amps, R1 is 3 ohms. All right, 10 amps, 3 ohms. 10 times 3 is 30 volts. So V1 is 30 volts. And now there's two ways you could figure out the missing voltage here. You know that the total is 60. All right, and you know, I'll erase this up here, you know that for a series circuit, V total equals V1 plus V2. So if V total is 60 volts and V1 is 30 volts, all right, how much is V2? All right, you can subtract 30 from both sides, and you know that V2 is 30 volts. Okay, now, you know it's 30 volts. You could also here say, well, if I2 is 10 amps and R2 is 3 ohms, then, all right, 10 amps and 3 ohms, then V2, just like V1, is also 30 volts. So we figured that out two different ways. Okay? So I'm going to leave that. All right. So using the equations for the total voltages for series circuit and using Ohm's Law, we were able to fill in every V, every I, every R for each part, each component of the circuit. The battery, VIR, totals, all right? This resistor, V1, I1, R1, and the second resistor, V2, I2, R2. All right? So, here's our next series circuit, and for this series circuit, the two resistors are not going to have the same resistance. In the last series circuit, this was 3 ohms, and this was 3 ohms. For this series circuit, this will be a 2 ohm resistor, and this will be a 6 ohm resistor. Let's start filling in all the other information that we have. All right, we've got here V total, we've got I total, R total, and P total. All right, for this first resistor here, we've got V1, we've got I1, we've got R1, we've got P1. For this resistor here, we've got V2, we've got I2, we've got R2, we've got P2. All right? VIRP, VIRP. Now, the information we have at the beginning of the problem, all right, the total voltage, the voltage of the battery, is 32 volts. And the voltage, the resistance for this resistor is 2 ohms. All right, 2 ohms. And this resistor is 6 ohms. Okay, so let's start filling in all of the other variables. We've got R1 and R2. We can add them together to get the total resistance for this series circuit. R total, right, is the same as REQ. The equivalent resistance is the total resistance. I like to use the capital T. All right, so the total resistance is going to be R1 plus R2. R1 is 2 ohms. R2 is 6 ohms. All right, so our total is going to be 8 ohms. Okay? So our total is 8 ohms. All right, now, we've got V total and R total. Let's find I total. Use Ohm's Law. All right, R equals V over I. Remember, whenever you're working with circuits, you're using a combination of the series circuit total equations, I total, V total, R total, and Ohm's Law to solve everything. You just keep finding more stuff until you got everything all filled in. All right, now, we want I total, so I'm going to switch I and R, switch the inverses. I goes up here, R goes down there. All right, I equals V over I. We're trying to find I total, so I total equals V total over R total. All right, V total is 32 volts. R total is 8 ohms. That means that the current is 4 amps. The total current is 4 amps. Now, this is a series circuit, so the total current is the same as I1 and the same as I2. So I1 is also 4 amps, and I2 is also 4 amps. All right, now that we have the current and the resistance for the first resistor, we can find the voltage of the first resistor. All right, V, we're going to cross multiply, put this over 1. V times 1, V equals I times R. V equals I times R. If you want to find the first resistor, it's V1 equals I1 R1. Okay, we'll just give him this little pat in his feet. Okay. V1 equals I1 R1. All right, let's get that over here. All right, so now, I1 is 4 amps. All right, R1 is 2 ohms. So, V1 is 8 volts. All right, so this here is 8 volts. Okay, let's do this one. All right, V2 equals I2 R2. All right, I2 is 4 amps. It's the same as I total. R2 is 6 ohms. 6 ohms. That means V2 is 24 volts. V2 is 24 volts. Now, just double check that V total is V1 plus V2. V1 is 8 volts, V2 is 24 volts. All right, and 8 volts plus 24 volts is going to be equal to a total of 32 volts. Okay? So we got everything filled in. Everything checks out. Okay? So go ahead and practice on the next two practice series circuit problems, and I'll see you in the next video.